Good morning. We are talking about the matrix analysis approach, especially the flexibility based approach right now. In the last lecture, if you remember, I talked about the fact that in SI was equal to BI into R, where R is the loading corresponding to the degrees of freedom, in which case it's essentially joint, because degrees of freedom are defined as joints. In addition to that, you have, as I was saying, this, and we were discussing that why we need this additional term which we didn't need. See, we were looking at this, we had solved this problem. And we didn't have anything here. But when I looked at this problem, okay, when I looked at this problem, I did not have a SIO. Remember, we did not use any SIO, we just did use SI equal to BIR and solve the problem. Okay, but as soon as I came here, I said, look, there is an SIO. What is the actual difference between the two? In this case, I don't have an SIO, in this case, I have an SIO. Let's actually look at this. Let's forget this 10 kilonewton, because 10 kilonewton is coming here, okay, and anyway its superposition is valid, and therefore you do not have a problem in putting it together. So let's just consider the 240 kilonewton loads and see what happens, which in this case we do not have any SIO. Why? Well, let's see. Let's solve it. You will see that you will get 20 kilonewton, 20 kilonewton. This is equal to 0. And therefore, if you look at the bending moment diagram, these two, the bending moments are 0, and the bending moment over here turns out to be . Remember, these were all 5 meters length. Every one of them is 5 meter length. Okay, so this is how the bending moment diagram looks. If you look at it, okay, what are the member end moments over here due to this load? You will see that the member end moments at all points are 0, and therefore actually the reason why we did not consider was this was 0 for all the members. Okay. However, if you look at this, right, if you look at this and you have 40 kilonewton load here. Now let's try to see what happens. Well, you will see first of all that there's going to be 40 kilonewton load here, and due to this 100 you will have right? And now let's draw the bending moment due to this. You will see just this one alone. You will see that you get something like this. This value is 200 kilonewton meter, and the same value over here. Okay, and then this one reduces it, okay, so that over here it goes from 200 to 100 kilonewton meter, and this is in this fashion, and ultimately here also this is going to be 100, all right, and this is going to be in this fashion. So over here 100, this is going to be 0. Okay, so it's going to be 0 from here to here, and from here to here it's like this. So this is going to be equal to 100. This is the bending moment. This is the bending moment diagram due to this. And therefore you see that even if we don't have any Ri, you're going to have Si. So if this is 1, this is member 2, this is member 3, you will see that for S1, 0, it will look like 0 to 100. For S2, 0, it's going to be equal to minus 200 plus 100, and for S3, 0, it is going to be minus 100. So these are, you see, this is the point that I am trying to make, that typically you have bending moments which, if you look at it, in this particular case R is equal to 0, and therefore Si into Bi R is equal to 0. However, this is not 0 because you have this. So therefore there has to be an additional term which takes care of this aspect. Okay? In this particular case we did not have it because this happened to be 0. Okay? So once you put that in, essentially again we come back to the fact that once Si is equal to BIR plus Si0, okay, this implies R is equal to summed up over all the members of Bi transpose Fi Bi. This part is the F, the structure flexibility matrix, plus summed up over all the members Bi Fi into Si0 plus summed up over all the members Bi transpose Vi0. Now understand that this is relating the joint loads to the joint displacements. This is directly given by Fr. Then in addition to that, this aspect is only happens if you have a member load that gives rise to bending moments at the member ends. So this is the effect of the member, and this is the additional effect of the member rotations due to the member load. Okay? So all these together account for, and this is the total for the flexibility approach. Okay, for statically determinate structures. Okay, so what you have in here is that we have set up how to get the member forces as well as the joint displacements using the flexibility approach. Okay, but this essentially, if you look at it, is true for a statically determinate structure, because we said that you can actually solve for SI given the loads. Okay. Now, how can we extend this to include the effect of statically indeterminate? Okay. So we are now using the flexibility approach for statically indeterminate structures. How do we apply this? Well, in reality, it's actually very, very simple. The reason behind it is that, well, even in a statically indeterminate structure, what do? You identify, see, in the statically indeterminate, if you go back, you determine static indeterminacy to identify redundant forces. Then once you identify the redundant forces, redundant forces equal to 0 implies statically determinate base structure. Okay, so since you have that, you see all that we've developed over here, the only additional things, let's see what happens. Sorry. Let us okay, exactly the same problem, okay, accepting that it is statically indeterminate. What is the level of static indeterminacy? You will see I'm not going to again go through the process. I have spent enough time. Static indeterminacy equal to 1. Okay. So then identify redundant force. Identify redundant force. And once you identify the redundant force, let me say that my redundant force, since it's 1, I will identify this as my x1. In other words, this is the force that I am making redundant. So as soon as I put that equal to 0, what is the structure that I get? This is my base structure. This is my base statically determinate structure. And if you look at this structure, this is identical to the structure that we have just solved in the last lecture, isn't it? Okay? So we have taken a statically indeterminate structure. What is the difference? Well, the difference is, in this particular case, let's see what the difference is. In the previous case, what did we do? We found out, we took this load and we found out the displacement at this point, and we found out the horizontal displacement at this point and the horizontal displacement at this point. In this particular case, I'm going to do exactly the same thing. I am going to find out right. So now, how would you solve this problem in the original situation? Well, you would find out, due to these loads, you would find out this displacement. Now remember, I called it R1 and R2 this time. However, in this particular case, I'll call this X1. What is the reason behind it calling it X1? Because in this particular case, remember that this is the degree of freedom associated with the redundant force. Okay, and since it is the redundant force, I'll give it a different notation. But as far as I've just given it a different notation, but as far as I'm concerned, it still is, you see, R1, R2 in the previous case is identical to what I am calling as R1, X1. Is that clear? Okay. Now, so you would find out X1 here, right? You would find out the displacement here. That's the step. I'm just going through the steps. So you would find out the displacement here. What is the next step? The next step would be you apply a unit force over here, find out what? The displacement at this point, right? So therefore, then we can say that, look, this would be x1 0, and I would say that f1 x1, what is this? This is the displacement at this point due to x1 equal to 1. So then you would say f1 into x1 is the displacement at this particular point, plus x1 0 is equal to 0, right? That this is the compatibility condition that you would satisfy under in the normal force method, right? In this particular case, understand this, that this problem, once this is the case, then note that all that happens in this particular case is In the original case, we had R1, R2. In this case, this becomes R1 and R2 is my redundant force. Okay. In the previous case, this was equal to 10 and this was equal to 0. This was what we knew because it was a statically determinate structure. In this particular case, this would still be 10. This is unknown. Unknown. Okay? This is unknown. But you look at this. R1, R2 is equal to R1, X1. This is the statically determinate case in the previous case. This is the current case. Here, this and this both were unknown. In this case, this is unknown. This is equal to 0 because I am considering the effect of x1 and r1. This is 0. So this is a kind of a problem in which, if you really look at it, see, for now I am not solving this particular problem because we have already found out this thing for this. So in the earlier case, what we had was for each member, what would you do? You would find out SI is equal to BI into R plus SI0. Understand that once I accept that X1 is a redundant load, okay, it behaves exactly like an external load. The only problem with X1 is that whereas for most other situations we know the unknown, we know the loads, here X1 is a load which we do not know. Okay, so here this one I can write it in this fashion. I can write it as S1 S2 is equal to, in the previous case this would turn S1 and S2 I would turn out to be equal to B11, B12, sorry, no, B21, B22, R1, R2 plus S1, S2, this is I0. Okay, in this case all that happens, and remember we computed this. How did we compute this? We computed this by putting R1 equal to 1 and finding out what the member end moments were, and we found this by putting R2 equal to 1 and finding out what the member end moments are. Okay, so therefore in this particular case here understand that R2 is X1. So here all that would happen is S1, S2 B1 B1 X BX1 BXX R1 X1 plus this still remains the same because this is nothing but the effect of the loads. No difference. Absolutely. These two are identical to these. This is equal to this, this is equal to this. The only thing is that whereas in the previous case, since R2 was an external load for a statically determinate structure, R2 was a determinate load. Now we have exactly the same statically determinate structure, excepting that X1 is a redundant force and therefore unknown. Okay? So therefore, if I go through this step, I can say that this is equal to BI R plus BI X plus S 0. Do you see this? And since this is nothing but r and x together, so therefore you see I can actually write it in this fashion. I am going to say that r is equal to r f x r f x x r vector x vector, and here this is x vector plus, and then I am going to put it inside all the standard items, which is bi transpose fi si 0 plus I bi transpose vi 0. Note that this equation that I am writing is for the base statically determinate structure. So this is identical to what we had for the statically determinate structure, excepting for a small problem, and that is that in this particular case we know these, but we don't know these. These of course are known all. We can find these out. You will see that since the flexibility matrix is symmetric, you will see that this is true. Okay? Now, I don't know this. However, compatibility conditions give me that I know this. So here you will see this problem. I know this. I don't know this. So if I rewrite this, you will see that I get it equal to, you will see that this bi will include both the effect of r as well as x. Okay, so I didn't want to write down those details. I'll show you what I mean when I solve a particular problem in a little while. Okay, so if you look at this particular thing, okay, you will see that this can be written in this form. The top equation will become, the top set of equations will become r is equal to FRR R plus FRX X plus summation. Now these are just the I corresponding to the R. Fi, this is nothing but the structure level, so this does not have anything to do, plus summed over all the length only due to the R. So this is the part of the matrix which belongs to only the R's. Okay, you will see that, in other words, Bi can actually be segregated into BIR and BIX. BIR and sorry, I'm very sorry. This should actually be, this is not, it is this way. BIR and BIX. This corresponds to the internal forces due to the external loads, and these are the internal forces due to a unit redundant. Okay, so this is equal to BI transpose FI VI 0, and you will see X is equal to FXR, which I'll call it as FRX transpose into R plus Fx6 into X transpose plus BIX trans. When you do transpose, you will see that this implies that BI transpose is going to be equal to BIR transpose BIX transpose. So that's how it happens. BIXI transpose FI SI 0 plus BIX transpose into VI 0. And note that typically this is a 0. Typically, okay, this is a 0 vector. So therefore, I can write this as minus Fx is equal to Frx transpose R plus note that I know this, 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 and I know this. So I can solve this for xi. Once I solve for xi, I can substitute that in here and I can get the displacements. Note that what about my SI? Okay, if you look at it, I found out the displacements and my SI is given by, how are they given? I've already done it. It is given by BIR into R plus BIX into X plus SI0. Note, this is known, this is known, this is known, this is known, and this is solved. Therefore, I can find out my member forces in statically indeterminate structure. Therefore, you see the beauty of this is known as the matrix force method. The beauty of the matrix approach is that the force method becomes a part of the flexibility, overall flexibility approach. We are not having to derive it separately. Okay, and therefore the redundant force is just treated as another additional load of course, which we don't know. However, we know the displacement corresponding to that load. Okay, so we can always solve for it. So this is the major advantage, that the compatibility equation that we get in the force method really is part of the entire flexibility method in itself. Okay, so I think this is, once you've understood this, it is very easy to understand that there is absolutely no problem in trying to find out using the matrix approach in the force method. So what I am going to now do is essentially start off a problem. I'm not going to be able to solve the entire problem. We'll continue into the next lecture, but I want to tell you, look at a problem in its entirety and solve it. Okay, so now what I'm going to do is, up till now I have just only briefly discussed this problem, but now I'm going to actually solve So let us take this problem and solve it in its entirety. Okay, so this is my member 1, member 2, member 3. This is A, B, C and D. All the members have the same EI and all of them are 5 meter length. This is at the center. All of them are the same EI. Okay, and the problem is one, find horizontal sway displacement of the top to find support reactions and find support reactions and member and moments and bending moment diagram. Okay, so this is the problem statement, and we are going to be using the matrix force method. So we're going to be using the matrix force method. Okay. So let's see. Already we know that this is a single degree of freedom. We've identified the redundant force, and therefore let us see . Since I need to find out this displacement and this displacement, these are the two displacements, because why do I need to find out this displacement? Because this displacement is what I've been asked to find out. Why do I need to find out this displacement? Because this is the displacement which is going to be equal to 0 in the original structure. Okay, and so now we are finding this out. So how are we going to find this out? Well, we go through the steps. The steps are: first, find out Vi0 and Si0 for the loading. Okay, and remember Vi0 and Si0 are only found out for member loads. Okay, and which is the only member load here? The only member load is this. So this gives rise to this and this, and so we know that Si0 is going to be equal to 0. We've already discussed this, so there's no point each one of them, all of them, for I equal to 1, 2, 3. So now I have to find out Vi0. Now Vi0 will only happen in the members that, so Vi0 is equal to 0 for I equal to 1 and 3. Okay, and for V20 we find out this is the member given this load. Okay, what is the so here you have 50 and we have V, this displacement, this is going to be my, so this is going to be my V V1 of 20, 20, and this is going to be V2 of 20. So V1 and V2, of 20 and 20 are equal to, we've already done this, I'm just going to put down the numbers. It's going to be equal to V10 is going to be minus 50 into 2.5 divided by 2EI, and this is going to be equal to plus 50 into 2.5 upon 2EI. We've already found this out. I'm just putting them down. Okay, so we found out V1 and V20, and then what are the next steps? The next steps are to find out the BIs. Okay. Now if I put this, I get this equal to 1. This is going to be this way, so 1, 1, and therefore if you will look at it, you will get that this is equal to 5 and this is equal to 5. This one goes this way and this one goes this way. We've already done this, so I'm just putting down everything properly. So here my S, you will see that B1 R is equal to 0, 5 B 2R is equal to minus 5 0 and zero zero. There's nothing new, but I'm just going through the steps again because I want to solve the entire problem. Okay. Now put remember that in the first method we are doing everything to the base statically determinate structure. So therefore there's nothing, I mean always I'm actually solving for this. Okay. Here was the next step, put x1 equal to 1 and find out what the thing will look like. If you look at this, this is going to be like this, these are going to be 0 0 and therefore what you have is all these I recommend that I am just putting them down as if I found it out, but if you don't know what I am talking about, I recommend that you go through and compute the bending moment yourself. Okay, so this is the bending moment for x1 equal to 1 and therefore B1x is equal to 0 5 B2x is equal to minus 5 plus 5 and B3x is equal to minus 5 0. Till now you have not seen anything that is different from what we have already done. Okay. So only thing is that I have identified this as x and the other one as r. Okay. So now let us go through the steps. So therefore just putting down everything, I have got S I0 are all of them for all I. Okay, V I0 is equal to 0 for I equal to 1 2 and V20 are equal to minus 62.5 EI plus 62.5 EI. So I've got my SIO, I've got my VIO. Okay, now what I need is my B. So P1R is equal to 0.5, B2R is equal to minus 5.0, B3R is equal to 0.0, B1x is 0.5, B2x is equal to minus 5 plus 5 and B3x is equal to minus 5, 0. Now what? Now you will see that R is equal to B1R. I'm going back to the equation that I had written down. Remember that the equation that I had written down was that R was equal to, well, actually let's just put it BI R transpose Fi summed up over all the I, BIR into R plus BIX transpose Fi, sorry, BIR transpose BIX X plus BI transpose, in this case SI 0, so all I am left with is BI transpose, so this is going to be equal to BIR VIO. Okay? And similarly X, if I put X here, I will get BIX FI BIRR plus BIX FI BIX X plus BIX VIO. Okay, and then we put X equal to 0 and we can solve for the problem. I'm going to actually solve this problem in the next lecture. Okay, so just wanted to introduce the entire concept, and I hope you are beginning to appreciate all the things that I have been talking about for now. Thank you very much. See you in the next lecture. Bye.